Welcome to today's video on equilibrium using ice tables. The learning target for today's video is that we should be able to solve equilibrium problems using an ice table. So what is an ice table? Ice tables are used to calculate equilibrium concentrations of the reactants and the products from the initial concentrations. Here are the steps that I used to use an ice table. The I in ice stands for initial. This means that I need to write down my initial concentrations, which is what I'm starting with originally at the very beginning of the reaction, and anything else I know, if I know any other equilibrium concentrations, of all species in my equilibrium expression. The C stands for change. I need to determine the concentration change for the species where the initial is known. And stoichiometry is going to apply here. I'm going to use my stoichiometric coefficients to calculate concentration changes for all other species in my equilibrium. And the E stands for equilibrium. Now I need to calculate what my equilibrium concentrations are. So let's dive into an example. Here's example 1. Enough ammonia is dissolved in 5 liters of water at 25 degrees Celsius to produce a solution that is 0.0124 molar ammonia. The solution is then allowed to come to equilibrium. Analysis of the equilibrium mixture shows that the concentration of hydroxide is 4.64 times 10 to the negative 4 molar. I need to calculate KEQ at 25 degrees Celsius for this reaction. What it's not asking me is I need my equilibrium concentrations of every substance in my equation if I'm going to calculate KEQ. So recognize that there's something in this question that it's not directly asking, but you need very much to calculate KEQ. So here's what we're going to do. We're going to make a table. Initial change in equilibrium is down on the left-hand column. I list every substance at the top, but really I don't need to list water because water is a liquid and water is not going to be included in my equilibrium expression. I go back and I write down what I was given from the information in the problem. My initial concentration of ammonia was 0.0124 molar. But it also told me that at equilibrium, the concentration of hydroxide was 4.64 times 10 to the negative 4 molar. My starting concentrations of ammonium and hydroxide were 0 molar because it didn't give me any other information about that, so I'm assuming it was 0. So what my change is I'm taking away from the reactant side and I have to shift it towards the product side. Why is it shifted towards the product side? Because I initially started with 0 products, so the equilibrium has to shift in that direction. So I'm going to take away reactants and I'm going to add to the product side. My coefficients here are all 1, so it's all 1s in front of the x's, so it's all relatively the same quantity of x. But now on my equilibrium, I know the equilibrium concentration of hydroxide. It's telling me it's 4.64 times 10 to the negative 4 molar. So that must mean that's what X is. I can go in and then calculate what my other concentrations are. So ammonia then, if I subtract X, I get my equilibrium concentration as shown, and my ammonium concentration is the same as my hydroxide concentration. Now that I know my equilibrium concentrations, I can plug them into my equilibrium expression, which again does not include water because water is a liquid. I plug it in and my K value is shown below, 1.81 times 10 to the negative 5. Okay, that was a relatively simple example, not too much extra math or extra steps involved, so let's do another example here. And this one's on your paper too. When hydrogen iodide is placed in a closed container, it will decompose into its elements, hydrogen and iodine, and an equilibrium will be established. So my equation is shown. It's telling me my initial concentration of HI, and it's telling me my equilibrium constant. So I don't need to calculate that here. What I need to find are my equilibrium concentrations. Okay, so let's make another ice table. I fill in my substances in order, reactants to products, and I fill in what I know. I know my initial concentration of HI was 0.025 molar. It didn't tell me anything about hydrogen and iodine, so I'm going to assume again that it's 0. That means my change I have to take away from the reactants and I have to add to the products. Now, why is it 2x right now? The 2 comes from the coefficient in front of HI. We had coefficients of 1 in the previous example, and so I didn't need to write them down. But now here it's a 2x. Hydrogen and iodine are both 1s in front of them, so here it's just plus 1x. But hydrogen iodide, it's important to know that it's minus 2x. So now my equilibrium concentration involves a little bit of a change. Hydrogen and iodine are both going to be equal to x. I can write down my equilibrium expression. Concentration of H2 times the concentration of I2 over the concentration of HI squared. I have equilibrium concentrations, they just have x's in them, so I can just substitute in what those are for right now because they equal the equilibrium constant, which was 2.23 times 10 to the negative 3. If I take the square root of both sides, that solves the square problem on my equilibrium expression side. And then I solve for the square root. I rearrange, I need to solve for x, and x is going to be equal to 1.1 times 10 to the negative 3. You can pause the video and double check that math at any time to make sure that you also get the correct value of x. But what that means is x is your change, right? So now I need to actually calculate what the equilibrium concentrations are. So the equilibrium concentrations for HI, when I subtract 2 times x, I get 0.023 molar, and hydrogen concentration is going to equal the iodine concentration, which is equal to x. Let's do one more example, and this one has a few more steps to it. So here's our example. A 5-liter flask is filled with 5 times 10 to the negative 3 moles of hydrogen and 1 times 10 to the negative 2 moles of iodine at 448 degrees Celsius. The value of my equilibrium constant is 1.33. What are the concentrations of each substance at equilibrium? It's a similar looking equation to before, but now we've flipped it, and obviously my initial concentrations are different. It's at a different temperature, and so it's a different problem. What I need to recognize right now is that I do not have concentrations. I have liters and I have moles, so I need to calculate my initial concentrations of each substance. I'll let you pause the video and you can do that now. Once you're done calculating your concentrations, let's make an ice table and put your concentrations into your ice table. So hopefully you found that the concentration of hydrogen is 1 times 10 to the negative 3 molar, and let's pay attention to sig figs also. Iodine is 2 times 10 to the negative 3 molar, and the concentration of HI was 0. It didn't tell me anything about that, so we'll assume it's 0. I need to take away from the reactant, so minus x, but then plus 2x, again for the same reason as we referenced before. The 2 comes from the coefficient in front of HI. And so my equilibrium concentration is as follows. I'm subtracting x from both hydrogen and iodine, and then I'm adding 2x to HI. Here's my equilibrium expression. And now I plug in my equilibrium concentrations, which we know have x's in them, into that equation. And this is where it's going to get a little trickier to solve this problem. You can pause the video here and use the solver button on your graphing calculator if you have one, or you can slog through and actually solve the quadratic equation, but we'll see the results of the calculations here in just a couple minutes. So if I take 4x squared, that's going to equal 1.33, and then the rest of my equation there, x squared, 3 times 10 to the negative 3 times x, plus 2 times 10 to the negative 6. Again, pause at any time and just double check the calculations and make sure that you're getting the same thing. If I rearrange for 0, or solve for 0. Now it's in the form of a quadratic formula. And again, you can pause, solve the quadratic, or look up a reference video on how to use the solver on your graphing calculator. I put a video link on my website for that. And we're going to find out that for my quadratic equation, x is going to equal 2 possible values, but only one of them is correct. X is equal either to 5.00 times 10 to the negative 4 or negative 1.99 times 10 to the negative 3. X cannot be negative because I cannot have a negative concentration in any of my reactions, so that must mean x is equal to the positive value, 5.00 times 10 to the negative 4. If I plug in that value for x in my equilibrium concentrations, I get my equilibrium concentrations, and they are as follows. Hydrogen is equal to 5.00 times 10 to the negative 4 molar. Iodine is equal to 1.5 times 10 to the negative 3 molar. And HI is equal to 1 times 10 to the negative 3 molar. So that had a lot more meat and a lot more math in it, but if you get the basic gist of how to write an ice table and how to solve for the equilibrium concentrations given any conditions, that is the purpose of this video. So try a couple practice problems on your own, and we'll see you back in class tomorrow.